Hi everyone, today we're diving into a very common and often overlooked phenomenon in electronics, the bounce effect of a push button. We will use LTspice to simulate and truly understand this effect, which can cause real headaches in digital circuits. Let's get started. When you press a simple push button, you expect a clean, instant on-off signal. However, the mechanical contacts inside the button don't make perfect contact immediately. Instead, they literally bounce against each other for a short period, typically a few milliseconds. This creates multiple rapid open and close transitions. A fast microcontroller or digital logic circuit can interpret these bounces as several presses, not just one. This leads to unexpected behavior and errors in your designs. To see this in action, we will set up a simulation in LTspice. First, we need a simple circuit. We will use a voltage source, representing our power supply, and a pull-up resistor. This resistor ensures our output is held high when the button is not pressed. Then, we will connect a switch to ground. This switch will simulate our push button. The output will be taken from the node between the pull-up resistor and the switch. Next, to model the bounce, we won't use a simple ideal switch. Instead, we can use a voltage source with a specific waveform to drive our input or represent the button's output directly. A powerful way to do this is with a piecewise linear, or PWL, voltage source. We will define a series of points that illustrate the bouncing. We'll start with the button in its unpressed, high state. Then, we'll define points that show an initial transition to low, followed by several very quick back and forth voltage changes, representing the physical bounces, before finally settling firmly in the low, pressed state. For example, the voltage might go from 5V to 0V, then quickly back to 5V, then 0V again, several times, all within a few milliseconds, before staying at 0V. This PWL source will perfectly mimic the noisy output of a real, bouncing button. Now, we'll run a transient simulation. We need to simulate for a short duration, perhaps 20 or 50 milliseconds, to clearly capture the bounce event. Once the simulation runs, we will probe the output node. On the waveform viewer, you will clearly see the voltage rapidly fluctuating up and down. It won't be a clean, sharp drop from high to low. Instead, you'll observe several peaks and troughs during the transition period. These represent the mechanical bouncing of the button contacts. This visual confirmation is crucial. It vividly demonstrates why debouncing is absolutely necessary in most digital systems. Without debouncing, a single button press could increment a counter multiple times, toggle a state unexpectedly, or trigger an interrupt too often, leading to unreliable system behavior. That wraps up our exploration of the push-button bounce effect in LTspice. We've seen how simple mechanical contacts can create complex and problematic digital signals. Understanding this phenomenon is the essential first step towards designing robust and reliable electronic systems. Thank you so much for watching and for spending your time with me today. If you found this video helpful and learned something new, please consider giving it a thumbs up. And don't forget to subscribe to the channel for more electronics tutorials, simulations, and project insights. We will see you in the next one.